Okay, so today's notes are on 7.2, the natural base E. So this is going to sort of introduce us into our log properties. And so one of the things that we first have to discuss is this new number. So a lot of numbers in math are not numbers, but we associate them with symbols. Like, for example, pi. Pi, though a symbol, is an actual value. It's 3.1415. And I. I is another one that's a symbol, or it's a letter, but I represents an actual value, and that's the square root of -1. A new one that we're going to introduce today, which we're going to use quite a bit in the rest of this unit, is this what we call the natural base E. The natural base E is an irrational number that is, let's say E is approximately 2.71828. And it's irrational because that decimal keeps going on forever. so that's E. E does have a value, so when you see E, it is an actual number. So just like any other number, it does follow the same exponent properties that we discussed last unit. So if you look at these examples here, if you have e to the third times e to the sixth, it acts just like a regular base. So when multiplying things with the same base, you just add our exponents. So this would be e to the ninth. Same thing here when you're dividing. So 16 divided by 4 is 4, and then you subtract your exponents, e to the fifth and e to the fourth, subtract to be e to the first, or just e. Same thing here, when I distribute this, I have to distribute to both of these exponents here. So that's 3 squared, which is 9, and then 2 times negative 4x would be negative 8x. So same properties, multiplying, dividing, power to a power, everything. E still works for all of those. Where E comes in is with exponential functions, and that's why we're talking about them within this unit. E is another form of exponential growth or decay. It's just a slightly different formula than what you used in the previous section. Here, the natural base functions will use or uses the natural base E. Oops, spelled that wrong. Natural base E. And the function is y equals a e to the kt. So you can see some similarities from the previous section. In the previous section, your exponential form was a b to the t power, a b to the t power, where this is a e to the kt power, and you see that k there. We'll talk about that k here in a minute. K, exponential growth, that k value will tell you whether you have exponential growth or decay. Unlike the regular exponential functions where the base would tell you whether it was increasing or decreasing, or growing up or going down, or growth or decay. In exponential with natural base exponential functions, the k value actually tells you whether it is growth or decay. If the k value is greater than 0, you have growth. And if you have decay, when k is less than 0. So, again, just like before, and if you want to, you can label these, but they're the same labels from before. A still represents initial value. I'll just put initial, and sorry guys, I forgot to move up there. So here's the y equals a e to the kt. It uses the natural base e, and a is still your initial. Exponential growth is when k is greater than 0. Exponential decay is when k is less than 0. So this is your initial value. K is going to represent the growth rate. Again, if it is greater than 0, then it will be increasing. And if it's less than 0, it'll be decreasing. And t, sort of universal here, is time. And so you can see the graphs here just to see. So when k, see, and here you don't see k, e to the x means, if you don't see k, then we assume k is 1. Being that it's greater than 0, you see it increase. Whereas here, I don't know if you can see that very well, but you might be able to on your notes, but this is e to the negative x, assuming that k is negative 1, which is less than 0, and you can see that that graph does decrease. So this is where k would be greater than 0, and this would be when k is less than 0. Okay. Let's look at some examples. So what we're going to do is we're going to tell whether or not each represents growth or decay, then graph the function by creating a table, similar to what we did in the last section. So what we need to look for is the value of k. K is the number that will be in front of the x. Since you don't see anything there, we're going to assume that this is 1, or this is going to be positive, meaning that this is exponential growth. And you can plug in e into your calculator. So when you're going to put this in your graphing calculator and to create your tables, you can use e. So you just got to sort of find it. So if we pull out our graphing calculator here and we go to y equals, let me clear out old stuff there, and we do 1/2. If you have the new operating system, you can hit alpha y equals. That'll get you a fraction, so you can do 1/2, just like that. And then e is right above the natural log. If we look down here, you see the ln, you'll see the e to the x, it's right there. So you do have to hit second, and then that ln will get you the e exponential function, and then you just put in x. Now before I move on, let me show you what this would look like, because a lot of you are using either a Casio or a TI with an older operating system. To put a fraction in, you could first just change it to a decimal, so it should be 0.5. Or if you want to have the fraction in there, fractions in the older operating system need to be put in parentheses. So 1/2 would be parentheses 1 divided by 2, and that would represent 1/2. And then you can still do the e to the power of x, and it's the same thing. So when I don't need to graph this, but if you want to graph it just so you can look at it, we can see that it is exponential. Let me zoom 6 this so you can see it in a standard window. And same, so it looks similar to what you saw in the other exponential functions. So we're going to look at we're more concerned about the table, so I'm going to go to the table and look at my table of values. So you can see on my table it starts with -2. So I can put that. You can see with the e, you have a lot of decimals. So it's okay. So -2 is 0.068. 0.068. -1 is 0.184. 0 is 0.5. And that should be, you should recognize that. Remember, that's your initial value, and it's right here in your original function. And then 1 is 1.36. Oops, 36. And then 2 is 3.69. And then 3 is 10.04. Alright, so now we graph this. Put this aside. Okay, -2 is 0.068, very close to 0, but not quite. Remember, exponential functions, 99% of the exponential functions, unless there is some sort of vertical shift within the function here, they're going to approach 0, but never ever cross that. So be careful when you're graphing these, not to have your exponential function across the x-axis. -1 is 0.18, so just a little bit higher. Then you have 0.5, 1.36, Goes up there. 3.69, really moving up now, and 10.04. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So just above that. Really accelerates it, but we want to be careful with when we're drawing our exponentials not to cross the x-axis. So something like that. Let's try another one. Now look at one where we can see here we have the value of k is actually there. We can actually see it now, but it is negative. Because this right here is negative, we have exponential decay. And so we're going to do the same thing. We're going to plug this into our graphing calculator. So put this over here. Y equals, clear that out. I don't have a number in front, so I mean that's just 1, but you don't need to put it. So it just goes right into e to the negative 0.2x. Negative 0.2x. However you want to put that in, you can put that in. Graph this so you can just see it. Looks like it's going down. It is a exponential decay problem, so that should go down. And then we look at the table for our values. So negative 2 for this one is 1.49. Negative 1 is 1.22. 0 is 1, which is what we expect. It is the number, the initial value. Though we can't see it in front of the e here, it is assumed to be 1. 1 is 0.82. 2 is 0.67. And 3 is 0.55. So a little slow decrease here, but you'll see. Negative 2 is 1.49, and then 1.22, and then 1, and then 0.82, 0.67, 0.55. Really hard to sort of see the exponential. You really have to pay attention to the graph to know what it does. So I know that on this end, it's going to continue to approach the x-axis, but never cross it. On this side, it's going to go up, but go up kind of slowly. So something along those lines there. Okay. So, how do we use this in sort of modeling and sort of real-world application? So, one of the things that uses the natural base E is radioactive decay. This is huge. Anytime we say, oh, you know, that bone or whatever is tens of thousands of years old or millions of years old, or this, you know, artifact is certain amount of years old, or this rock is like 4 billion years old. The reason why that you can get those sort of dates is because some of the minerals in some rocks are radioactive and do decay over time. And if you can measure the amount of material that there is, you can sort of go back in time to figure out just how long ago or how long that whatever rock or bone or whatever has been decaying. So it is used a lot in dating things and stuff like that, especially with radioactive decay. Also in radiation with nuclear bombs and stuff like that, but it is used quite a bit. So a couple of the things here. It says tritium and sodium-22 decay over time. In a sample of tritium, the amount y in milligrams remaining after t years is given by the function y equals 10e to the negative 0.0562t. So we have a function for tritium. Okay, that is a function. And then the graph shows the amount of sodium-22 in the sample. So sodium-22, we don't have an equation for it. We just have this graph over here. All right. So we're going to sort of relate the equation with the graph and sort of make some inferences here. So A says which sample started with the greater amount. Well, this goes back to understanding your function and what represents what. You should know by now, after the last couple days, that the value that's in front here, and this works for regular exponentials as well as natural base E exponentials, but the number that's in front, this A value, this is your initial value. So for tritium, the initial value is 10, and the units are in milligrams, which is mg. Whereas With sodium, we have to sort of refer to the graph. The initial amount will represent the y-intercept, or I should say the y-intercept would represent the initial amount. So on our graph, we go here and we find the y-intercept and we sort of estimate that if this is 10, this is 20, then it's probably about 15. So sodium 22, starts out with about 15 milligrams. So which one starts out with a greater amount? This sodium 22. Sorry. B, which sample has a greater amount after 10 years? This is where we're going to need the function and to be able to look at 10 years and see where it's at, and whereas we have to compare it to the graph that's over here. For the equation one, this is quite simple because we can just plug it into our calculator. Y equals 10e to the negative 0.0562 t, or 10 for years. And we can just plug it in our calculator and see. So you can plug this straight into your calculator exactly as it's written. I could do 10 and then do the e button. E to the negative 0.0562 times 10. That's all you need to do. Type it straight in there and you see that it's 5.7 milligrams. So 5.7 milligrams. And that is, sorry, this is tritium. Now sodium, since we don't have an equation, we have to sort of estimate it. So to estimate it, we go to 10 years and we look up and sort of figure out, okay, well, here's where it is. It's right there. What is about that value? Well, if this is 5 and this is 10, then it's probably 1 to 2. We'll estimate it about 1. So sodium 22 is approximately 1 milligram. And so the amount, which sample has the greater amount after 10 years, that would be tritium. So just using some models, some graphs, some equations to sort of model some questions here and sort of make some inferences. But that's one way to model natural base E exponential equations. The other way is through compound interest. Now, in the last section, we talked about compound interest. These ones right here, we talked about compounding, quarterly, monthly, weekly, daily, and the different changes in that equation. If you start out with $1,000, the more times you compound, you see that the value does increase. These right here, and I'll just sort of draw that, would represent the original, which is A equals P, and then 1 plus R over N to the NT. That was the original equation for compounding. Now, these compounds of quarterly, monthly, weekly, and daily have specific amount of times that they are compounded over time or in 1 year. Quarterly is compounded 4 times per year. Monthly is 12 times per year, because there's 12 months in a year. And weekly is 52 times per year, because there are 52 weeks in a year. And daily is 365 times per year, because there are 365 days in a year. But what if you could compound it continuously? So imagine compounding your interest like every second or every fraction of a second. Maybe you calculate your new interest every millisecond. Okay, that's what we would call continuous, where it is compounding all the time. Compound. And, for that, we have to use the natural base E for our compound interest that compounds continuously. So the new equation for compounding interest that is continuous it's going to look similar to that one, though I think a little bit easier. A, same A from above, equals P, same P from above, principal, E to the RT. So much simpler than the other one, and similar sort of variables here, where A, just like before, represents your balance. Okay. P will represent your deposit or initial amount. R is your interest rate, but as a decimal. And T, again, obviously is time. More specifically in years, time is years. So when we get information about compounding, we just plug everything in. So I mean, we could do an example here. Find the balance in an account after 4 years. If you initially deposit $1,500 at an annual interest rate of 5.5%, compounded continuously. And there's that key word. If you see it compounded a specific amount of times, like quarterly, monthly, weekly, daily, then you would have to use the original function up here. But if you see the word continuously, you know that you need to use your continuous function, which is with the natural base e. So we're going to plug everything in. So I get, A equals my initial deposit of $1,500 will represent P. Okay. E to the rate, right here, rate, this would be R, but it's 0.055. You can see that, 0.055. So to the 0.055, and then 4 years will represent T, so times 4. And again, you can just plug that straight into your calculator just as it is. Okay, 1,500 E to the 0.055 times 4, and you get your amount. So I get 1869.12. And that would be the amount. That would be in the account. Okay. Now this one, number 2, says to choose which one is better. So 2 says you invest $2,500 in an account to save for college. Account 1 pays 6% annual interest compounded quarterly. Account 2 pays 4%, so less interest and compounded continuously. Which one should you choose to obtain the greater amount after 10 years? So we have 2 different types here. We have the 6%, which will represent R, annual interest compounded quarterly, which is 4, and that's N equals 4. Quarterly means I need to use the original equation. So when we have an initial deposit here of P. So for the first one, for account 1, I actually have to use the original equation, which is P times 1 plus R as a decimal, so 0.06 over N, which is the amount of times that it's compounded per year, and then to the NT, so 4 times, and we want to keep it in there for 10 years. Okay. So again, you can actually, I don't remember if I did this in the last video, but you can actually put that entire thing in your graphic calculator, especially if you have one of the newer operating system. It makes it real simple. So I can do 2,500 parenthesis 1 plus alpha y equals, for my fraction, 0.06 over 4. Now again, if you have the older operating system, you do the same thing, except you'll just put this part in another set of parentheses, 0.06 over 4. Parentheses, and then the exponent of 4 times 10. And so everything's in there, just as it looks. Enter, and there you go. 4535.05. So that one is for account 1. For account 2, same initial deposit, though it does pay 4% annual and is compounded continuously. So a different formula. For that one, I need to use the A equals PERT. P being 2,500, E to the R, which is 4%, so 0.04 times the same amount of years, and that is 10. So I'm going to plug that into my graphing calculator. Let's bring it over here. 2,500 E to the 0.04 times 10, so just how it looks there. hit enter, and I get A equals 3729.56. And so you can see it's a pretty big difference. They're in the account for the same amount of time, 10 years. You have the same initial deposit. The only difference really is that this has the 6% interest and this has a 4% interest. So a big difference, only 2 percentage points here, but a big difference in the outcome of the amount of money you have. All right, that's the natural base E. So we're going to work with a lot with that natural base E going forward. So let me know if you have any questions. Thanks.